is that you can actually, there is no shame in shift entering through the notebook. So if you get stuck, you can just go through the notebook, execute it. It should run until the end. There shouldn't be any point in which you get stuck. So if you want to go through it to arrive to parts that are easier for you or whatever, I mean, you can do that. It's not a problem. So I see that Hannes has joined, and I will promote him to panelist and allow him to talk. So great. So Hannes.
Yeah. Hello. Can you hear me?
Yeah, perfectly. Okay. So it's great to have you. So we'll now quickly go through the notebook and try to give you some insight into, I mean, how things can be done in different ways, or where you should focus typically in the tasks that we are doing, because we know that sometimes, I mean, things are complicated, right? And there's many ways to solve things. So what we'll do is that I will just shift enter my way through the notebook until we get to some points that might be worth spending some time with. So here I am. We go at the beginning, always remember to execute all cells, because otherwise things might not work. This is valid for these notebooks, but it's in general valid for Jupyter. So importing all libraries, executing these lines that are the ones that are allowing to see the plots in the notebook, color coding. Now, here, for example, you see that you have an error because this is a cell that it's supposed for you to check this kind of behavior. Shift tab, you can actually see what are supposed to be the options or the syntax of any given function. So let's move forward. Remember that list arrays in Python are zero index, meaning that the first element is 0. We have here a nice overview of our data set. You can get a lot of info about the data set. If you use the describe, you can get a lot of info about, for example, for each column, the standard deviation, the minimum, the maximum, and the percentiles, and all of these. Number of unique values, and you can see that you have different number of unique values. This is telling you that there might be differences between the two replicates of the experiment. So you have a different number of proteins in the two replicates. Of course, this is a problem, and we'll see how to face it. Since we don't have so much time, I think it's better if we go through everything. Question 1, what is the lowest value in sample tree? I mean, you can take these from here. It's sample tree. You see that the minimum, it's minus 1.69. So, great. So, I mean, there are some small problems with these questions. So if you didn't get the answer correctly, it's probably because you inserted more digits or less digits. Will make it more robust. We just realized that. Anyways, let's move forward. You have a lot of methods that you can use to visit your data. And it's in general, as a data scientist, what I always teach to my students is always look at the data. Don't trust the result of whatever script you're running. Always look at the data and get a feeling of the data. It's extremely important, and it will save you from hours and hours that are wasted if you realize after a lot of time that there was some problem with the data. So it's always...
maybe if I can add one thing. So if you're doing sequence analysis, this is a very valid point also, that often you have a set of aligned sequences, and many problems occur because something went wrong in that alignment step, and just looking at the alignment in an alignment viewer can really save you from months of pain.
Yeah, and we all know that because we've been there.
Yeah.
So great. Let's move forward. Log. I know it's painful. It's painful for everyone to learn how to use these kind of things. There's no way to make it better, unfortunately. You have to learn how to use these to access the data. But it's a worthy the effort, because then you can do a lot of manipulation on the data. And for example, here you can see what are the values in rows, in columns, and so on and so forth. Okay. And so, for example, I mean, this one was a bit confusing. What is the 35th protein ID? Always remember that the problem here is with arrays and lists. They start with number 0, right? So, for example, if we want to have the location of the 35th, you can, for example, do df row. And here you have many ways to do that. So let's suppose that we want to use ilog. And let's start with 0, 0. Okay, so here we are taking a single cell. So if we want the column, what is the 35th protein? I'm now printing a complete row, and we can see that the name that it's down here is this one. Okay, get used to these. It's a bit not super user-friendly, but once you get this kind of way to access the data, it's pretty straightforward. I will jump here because, I mean, it's all of the same. One nice thing that you can rename your columns and sort your columns in a different way. That's very useful when you have to create plots, because you don't want them to be sorted in a random way. We'll just Shift-Enter up to the interesting part, the missing values. Now, whenever you have missing values in your data, what you do to get rid of these might change quite drastically the outcome of your analysis, right? So what we did here is that we took 2 decisions. First of all, is that you can just decide to discard any, for example, protein that contains missing data. In some cases, I would say that this is acceptable. For example, if you have 10,000 samples in your data set and 5% have missing data, you can decide just to discard missing data. My main expertise is machine learning, and usually this is what we do. If you have enough data and you are not introducing any bias by discarding the samples that have missing data, you can just decide to do that. But this is...
Yeah, if I can just add one thing, that the problem is that this is something that rapidly goes wrong with increasing data set sizes, because if there's some risk that any one variable value is missing from any one of your data points, then the chance that that you will have missing values in a column increases to almost 100% as your data set grows. So with a reasonable sized data set, you will throw out all your data.
Yep. But exactly for these, I mean, there are ways to impute missing data. Imputing means that we put some numbers in the missing data. And what we do here is that we decided to do a mean imputing. Sorry, first there is some plotting here. So first of all, we perform some visualization of the data set. So before going to the imputing, let's have a look at this plot. These are this type of plots are called Boolean plots, and I really like them, and I really like the type of information that it can give you, because it's very easy to read these kind of plots, but at the same time, it's there's a lot of information without overloading the plot. So what we see here is that for each sample, Ni are not infected, day 3, and ECM it's day 8. We see the distribution of protein expression normalized as a log2 level. Now, you can see that there is a lot of variability, not only between different conditions, but also between different samples in the same condition. For example, Ni2, Ni1, and Ni7 and Ni8 are very different one to the other. So we can see that there is so much variability that is due to technical variability, to individual variability, that it's not really meaningful to compare things as they are. And I don't know if Anas, you want to?
Yeah, I mean, so the violin plot's very nice because you can actually see the distribution. So it's like a box plot on steroids. It's more informative, right? And also super important to be aware of this fact that there is variability in your data. There's both noise from measurement error or various issues along the entire path of steps that you take to get your measurements, but also, of course, there's the biological variability, which is what we're interested in, the difference between non-infected and infected the cells or animals in this case, for instance. And we want to somehow not be, we want to get rid of the technical noise, the technical variability. If one set of values is shifted upwards by some constant because of problems with the measurement, then we want to pull them down so that they're comparable, but in a way where we don't remove the biological signal. And that is the challenge in this sort of thing.
Yep. Great. So let's move to the next point. I mean, the time, unfortunately, is very short, so we have to rush through things, but empty values. So now we get to the imputing. Okay. So first of all, how many empty cells or empty values do we have in the data set? And we can see that it's quite a lot. So it's in the order of hundreds of rows that contain empty values. Basically, here what we will see is that it's too much data. We cannot throw this away, and it doesn't make sense. So what we do here is that we decided to use the so-called mean imputation. And you can read more here. There's so many ways to do imputation. Mean imputation is something that it's kind of a vanilla way to do imputation. Basically, what you say is that if you're missing the expression value for a protein or a gene in a given condition, you will use the mean of the value for that specific protein in all conditions. Why this is vanilla? Because basically, if you then do statistical tests to see if some protein is overexpressed or underexpressed, this shouldn't affect too much the statistical test. But it is also something that it's very risky to do, and I'll maybe chip it in later, especially if you want to do machine learning. But now we have here Anas, and Anas is the Bayesian guy. I don't know, is the Bayesian guy the good cop or the bad cop in this situation?
Definitely the good cop. Bayesian analysis is the only way to get at the truth of anything.
I knew that. So maybe you can give a Bayesian interpretation of imputing.
Yeah, I mean, so definitely. So in I think imputing is you should never throw. My take on this is you should never throw away data, because typically data is expensive, and you don't want to have less information. Pretend that you have less information than you actually have, but you need to then face the problem of the missing individual variables and given data points head on, and imputation of various kinds is the way to go there. And the problems are that if you do a simple sort of imputation, for instance, replacing all missing values with just the mean, some fixed value, then you are seriously underestimating the degree of variability in that variable. Suddenly, if you have 50% missing values and you put the same mean value on all of them, then you have much less variation in that variable than what is realistic. So that is something you need to think about. There are ways around that. For instance, something called stochastic imputation. There's a package in R called MICE, M-I-C-E, where you do multiple stochastic imputation. So you get 5 imputed data sets with some variability. Then you do the analysis on all 5. And then you at the end can get sort of an average and a standard deviation for your estimates. That's one way of not cheating yourself into thinking you're too certain of the thing. In the Bayesian world, we would just put in an extra parameter to estimate, and it would fall naturally into the Bayesian view of things, which I recommend you should actually do in the long run.
Yep. And also, I mean, to add on top of these, if you do machine learning and you do mean imputation, you will have that a specific protein has always the same value when you're imputing it, if you follow these. And it's much more common that you can imagine that, for example, you have more missing values in a positive data set, people with a disease with respect to the negative data set, people that are healthy. Since you don't want to throw away any data, you say, okay, I'll just do mean imputation. Then you train your machine learning algorithm to identify disease from healthy. And what the machine learning algorithm will learn is that you will have in the disease data set always the same value, or almost always the same value. And the predictor would work very nicely, but you're just fooling yourself. So be careful when you do imputation, because it might be very risky depending on what you want to do.
Yeah, you should do it in the right way. You should have something that adds a stochastic variability, so you don't put the exact same value every time. That's super important.
Yep. Another way to do this in a machine learning way is that you can also do imputation using random forest, but it's maybe, I mean, too advanced. So let's actually move forward now. We are almost out of time, and we can now visualize the data again. We see, I mean, the distributions have not changed because we have just introduced mean values. So of course, they are maybe a bit fat at the center, but they have not changed that much. But now we have the problem of comparing proteins in different conditions. As you can see, there is so much variability that if we would compare proteins in different conditions as it is, we will probably just be comparing background noise or differences in the experimental setup. So what you do is that you can normalize the data. And the way that we normalize here is by subtracting the mean and dividing by the standard deviation. This is a very, very, very common way to do things, and usually it's an okay way to do. Of course, if the original data had a normal distribution, this would do so that the normalized data is normally distributed with 0 mean and 1 standard deviation. But there are also other ways and other types of transformations that are meaningful in this situation. I can, for example, say that when you want to do machine learning, it's quite common to do some kind of normalization so that your data has a range between 0 and 1. That is usually something that you do a lot if you want to train a neural network, for example. Another thing that it's pretty common is that everyone is now familiar with the logarithmic scales. You all have seen these kind of models of exponential growth of the infection of SARS-CoV-2. And we know that if you plot these kind of models in a linear scale, you see exponential growth. If you plot them in a logarithmic scale, you see a linear growth. I would say that the way you transform the data really affects the model that then you are going to fit. For example, if you fit your model in a log transformed data, the points that are at the beginning of the curve and the points that are at the end will have equal weight. But if you fit the model in a linear, non-transformed data, the points that are later, when you have a lot of infections or a lot of people that have been hospitalized, will count much more in determining the model. So transformation are useful, extremely useful when you do data science, and they are meaningful based on the type of model that you believe it's underlying the data. Great. So I will just move forward. And we have here the normalized data. Now you can see that they all have a similar mean and standard deviation. Correlation using Spearman correlation and visualization using heat maps. This is a very nice tool for visualizing the data. I will go directly to this one. That is correlation matrix that is also including hierarchical clustering. So you see that you have each sample is compared to the others, and it's colored according to the similarity, the correlation to the others. So dark blue means that the samples are extremely similar, and they have a negative correlation, so that actually the proteins are following an inverse relationship. So proteins that are overexpressed in one sample are underexpressed in the other, and vice versa. So in general, this is a very powerful way to visualize similarity. And by looking at the dendrogram, so the hierarchical clustering, you can easily see which samples are very similar and which one are more diverse. Now, I think one thing that I want to say is that you have a lot of different ways to generate the hierarchical clustering. And this can vary quite a lot from one method to the other. But the nice thing is that when you visualize this kind of heat maps, you can see by yourself if there is actually a good similarity between samples or a bad similarity. So it actually gives an immediate feedback to understand if the clustering that you have performed is meaningful or not. So I think that, heat maps in general are super powerful tools and allows to get a feeling if the hierarchical clustering that you're doing is meaningful or not. So, great. I think we can also move forward here. PCA. Okay, PCA, it's a way to visualize highly dimensional data. It's a principal component analysis. The main idea here is that you have data that has a lot of dimensions. For example, in this case, each gene expression is one dimension, and it's kind of hard to visualize this type of highly dimensional data in a way that it's easy to understand. But what you want to do is that you want to understand what is driving the variability in each, for example, in each sample, right? So you will observe a lot of variability between genes, and you want to understand where this variability comes from. And you can do that by performing a principal component analysis. Basically, you identify directions in the data or components in the data that explain most of the variability. So the first dimension is a dimension that will try to explain as much variability as possible. The second dimension is the dimension that will explain as much of the remaining variability, and so on and so forth. Now, let's first try to see some of these variability. And we are looking here at the first two principal components, and we see that blue and green dots are all on the left, and red dots, that it's advanced day 8 state of the disease, are all on the right. Now, this is a very nice outcome for a PCA. So remember that the PCA doesn't take into account the labels or the state of the sample. So if we observe that the principal component 1, that is explaining most of the variability, is able to differentiate between samples in a biologically meaningful way, that's the best possible scenario, because you see that most of the variability in your data is actually connected to biologically relevant differences. But you should also be careful not to overinterpret PCA plots, right? So there are 2 or 3 main things that you have to notice. First is that how much of the variability is actually explained by the principal components. It's very important, right? So if you have that the first principal component is only explaining like 5% of the variability of your data, you have to be aware that you're looking at a very small subset or small part of the information that it's in your data. So it might, the things that you see might not be a complete picture of what's going on in the data. And second is that in some cases, if you don't see that the PCA analysis discriminates between positive samples and negative samples, it doesn't really mean that this piece of information is not in the data. It might be that the variability connected to technical replicates or noise or other type of variability are masking the signal, but the signal might still be there. So be aware that the fact that the PCA is not able to differentiate doesn't mean that the signal is not there. Anas, do you want to?
Yeah, no, that's true. There could be more complicated. I mean, so essentially, the PCA is looking for some linear combination, and if there's a non-linear interaction, like 2 genes, either one of them has to be there and the other one should not, then you won't. That's the sort of thing you won't see in a PCA. So things like that can confound it.
Yep. So take-home message for the PCAs: it's an extremely powerful tool, extremely useful. Just be careful. And one thing that you were mentioning before, Anas, is that
I mean, one thing maybe there is that if you see something like this in a PCA, then you know that you're good. That there's a set of genes whose combined, whose overexpression or expression pattern together has something to do with your biological signal. So that then you know for sure that there's something there, and you could then go in actually and do what's called a loading plot, add that to the PCA, and you would see which genes are actually driving principal component 1 here. That can be interesting. You can actually get a list of those genes. But if you don't see a signal, it could be for all sorts of reasons. If you do see a signal, you're good to go. If you don't, there might still be something there.
Mm-hmm. And you were mentioning the loadings. We have it here, and actually we can see that the first dimension explains 40% of the variability in the data. So that's a fair amount of variability that we are explaining with that dimension. So I would say that in general, this is a very nice example to see the power of a PCA. Okay, we are out of time, so we'll quickly go through volcano plots. It's the last part. And here there's so much to talk about. So I'm not an expert of gene expression or protein expression analysis, but volcano plots are quite a common way to identify things or to see things. The main idea is that you want to first to perform some kind of statistical test. And we're using a t-test with multiple test corrections. We don't have time to go through these. There will be a module on statistics, so we'll keep that for later. But we want to identify proteins that are overexpressed in specific conditions, right? And we perform the statistical test. A volcano plot is a way to represent these together. I'll just skim through it together with the fold expression. So in a volcano plot, you have an x-axis, you have the overexpression or underexpression of each specific protein. So each dot is a protein that can be either overexpressed or underexpressed on in a specific sample. But then, if you let's say that you have a protein that has a very, very low level of expression. Let's suppose that we are analyzing genes and from NGS data analysis, and you have only 2 reads that map on that gene in a specific condition when you do RNA-seq analysis, and you have 4 reads in a second condition. So you have a 2-fold increase of the expression. But the numbers are so low that it's probably due to just to background noise or to stochastic variations in the data, right? So you also want to have a feeling at the same time if the differences are meaningful. And this is what you see in the volcano plot. You have both the overexpression and underexpression, but also the Q value, that it's something that is derived from the probability. And in blue and red, you identify all the proteins that have overexpression or underexpression of at least 1. That means they are either twice as abundant or half as abundant in the condition with respect to the baseline. But you also see only the things that have a statistically significance. Now, in this case, the statistical significance, it's a very hard threshold. So you decide some kind of 2-fold overexpression or underexpression and a p-value of 0.05, for example, or a corrected p-value of 0.05. It's a very rough way to do things. And I believe that in a Bayesian way, you might have other ways to do that. Is it true, Hannes?
Yeah, I mean, so in the Bayesian world, we would not, we don't use p-values. We focus on estimating in this case, the fold change along with how much certainty we have in that estimate. But volcano plot is sort of the p-value world. It's a nice step in the right direction, I think, because there is that focus on the fold change. So having something super significant with a small fold change is just not interesting. So you should start by looking at the most overexpressed genes, and then it's nice to at the same time be able to see what is the statistical significance of those.
Super, great. So I think we are almost at the end. The last part of the notebook is about identifying what are the labels of these overexpressed and underexpressed genes, and try to see if there is some interesting biological features for them. This is something that typically people do. So it's not part of this notebook here, but this is kind of the typical end of this kind of analysis. So we have now gone through the whole notebook. Now, there is 5 minutes if you have questions, and we'll be happy to reply either live or through the chat. And to wrap up quickly, we'll be back at 1 o'clock then after and start the second notebook. Also, please remember the notebooks will be available for 1 week. So they will be online until Friday of the next week. So if you want to go through them and listen to the recordings and go through them, you have 1 more week to do so. Great. So we are now open for questions if you have any. Otherwise, I'll see you in 1 hour. Thanks. And thanks, Anders.
Yep, thanks. I just put in something in now. So I just put in, so if you have these lists of overexpressed genes like we get in this type of analysis, there are tools that will do what's called ontology analysis of it, looking into is there something common between the set of genes that or proteins that we find here. And I just put a link to one such such option called David, where you can automatically have it look through the gene identifiers and then say, yes, this has to do with amino acid synthesis or whatever. But there are several tools for this. This is just one.
Super. Is there any question? Thanks, Fred.
Yeah, Fred sent a better one there.
Great. Okay, if there's no question, we'll just go for our lunch and we'll see each other in 1 hour. Thanks a lot.
Okay. Bye-bye. See you.
See you.